Yeah, it's showing now. We can
Okay.
continue.
So where were we?
Chunks master.
Master. Yeah, master. The metadata stored at the master includes name and directory of each file, mapping of each file to its chunks, current location of chunks, access control information. The master also controls system-wide activities such as chunk lease management, locks on chunks with expiration, garbage collection of orphan chunks, and chunk migration between chunk servers. Master assigns chunk handle to chunks at time of chunk creation. The master periodically communicates with each chunk server in heartbeat messages to give it instructions and collect its state. For performance and fast random access, all metadata is stored in the master's main memory. This includes the entire file system namespace as well as all the name to chunk mappings. For fault tolerance and to handle a master crash, all metadata changes are written to the disk onto an operation log. This operation log is also replicated onto remote machines. The operation log is similar to a journal. Every operation to the file system is logged into this file. The master is a single point of failure. Hence, it replicates its data onto several remote machines so that the master can be readily restored on failure. The benefit of having a single centralized master is that it has a global view of the file system, and hence it can make optimum management decisions. For example, related to chunk placement. Client. Client is an entity that makes a read or write request to GFS. GSF, the typo there. GFS client library is linked into each application that uses GFS. This library communicates with the master for all metadata related operations, like creating or deleting files, looking up files, etc. To read or write data, the client interacts directly with the chunk servers that hold the data. Neither the client nor the chunk server caches file data. Client caches offer little benefit because most applications stream through huge files or have working sets too large to be cached. Chunk servers rely on the buffer cache in Linux to maintain frequently accessed data in memory. Next, you gotta go next.
Annie, can we rotate the reading?
Yeah, yeah, please.
Anyone wants to take up the reading?
I can read.
Let's have like like 20, 15, 20 minutes
Did
session so that
we
actually
discuss about
everyone gets.
client yesterday?
No, actually, we were supposed to discuss the master.
Master,
Uh,
right? Yeah.
yeah.
Master server is the coordinator of GFS cluster and is responsible for keeping track of file system metadata.
But I read this already.
No, no, we
Oh,
want to discuss, so we are
Ah, okay.
revisiting each point again.
Okay, got it, got it.
So the metadata which is stored on the master server has name directory of each file, mapping of each file to its chunk, current location of chunks, access control information. The master also controls system wide activities such as chunk lease management, logs on chunk with expiration, garbage collection of orphan chunks, and chunk migration between chunk servers. Master assign chunk handle to chunk at time of chunk creation.
So basically, chunk handles are nothing but unique way to identify the chunk ID, or it could be a serial number, or it could be some UUID. So, like the orange block we were seeing is nothing but the ID of the chunk, like uh, to basically uniquely identify a particular chunk. Now, this chunk will have copies, right? So that's why we are able to see the orange blocks in C1, C3, and C4. So let's say if we call 001 as one of the unique ID that represents one chunk, then 001, like the chunk handle one is there in C1, C3, and C4, like that. So effectively, the first file F1 is being split into three chunks, like chunk 1, 2, and 3, and each of them will have multiple copies.
You mean chunks 1, 3, and 4, right? C1, C3, C4, right?
No, no. Chunks for the file one is 1, 2, and 3. Basically, orange, purple, and
Oh, I see what you
the
mean. Okay,
yellow
got
one.
it.
Yeah.
Yes, got it, got it. And then the second file has two chunks, 4 and 5, right?
Yeah.
The blue and the red
Right.
on
Yeah.
the room.
Yeah.
Yeah.
Okay, yeah. So, what we are able to see in different colors are just the chunks, like separate chunks, or and then each of them will have a replica, like copies. So that's why basically they color coded it so that we can see that the blue part is we can see the blue part three times, like the chunk number 4, and similarly the pink part is three times. So so our replication, since our replication factor is 3. So these chunk handles are being assigned by the master initially during the chunk creation.
When the chunk will become orphaned, garbage collection of the chunk. When it will be
So any
orphaned.
file can be opened and then edited, right, or
Hmm.
deleted.
Yeah.
uh, so if a file is opened and then edited, then we won't be able to mutate the same file or the same chunk. Basically, we'll be rewriting the file into a separate, basically a new fresh copy of the file, which will be updated file. So the in that scenario, the existing file will expire, and or the
Chunk
existing
will
chunks
expire.
correspond.
So
Yeah, the
you
chunks
mean to
corresponding.
say, in this one, okay, one chunk one is present on one C1, C3, and C4, and whenever that update is happening to that chunk, that will be this is immutable. That's why a new chunk will be created, and this will become orphan and garbage collected. That and the new chunk will be written um, on these or some other chunk servers.
Yeah, correct. So if let's say if we modify the file, the first part of the file, then we'll be creating a chunk 6, which will be part of F1, the first file, and then one will become of orphan. Just reframing what you mentioned.
Okay. So file handle will sorry, chunk handle will also change, and one will become orphan, and it will be
It will
garbage
be a new
collected.
chunk altogether, right? It will be altogether creating a new chunk. So since the new chunk is created, it will be assigned a new UUID.
Okay.
So,
Must.
I mean, I repeat again, these systems are not to modify the files, only append only files. So the scenario when the chunk can be orphaned is that when you actually delete a file. So in that case, the delete will initially delete the metadata, and now that there is no relation, the chunk does not have any file in the master, then the scrubber on the back end will clean up these chunks.
Okay, so you mean like this it will never have the like the okay, I think I understood, like the immutability
Yeah,
we mentioned applies to the file, the whole file, and not to the chunk.
right, right. So once chunk is close, so then you can r- create only a new chunk, append to that only. You cannot actually modify somewhere in the middle of the file.
uh so you mean like that applies to all three of them, right? Like if you want to update the file, we have to basically scrap all three of them, right? And
When we call update, so this append only mutation. So you just append to that file. You don't actually make any changes in the middle. If you make any changes, that means you'll have to rid of all the existing chunk.
understood. Okay, okay.
Yeah.
I'm still little
Actually,
confused. So when we say append, does that mean it will be end of chunk 3? Or, I mean, I'm not clear about
Like let's say if 1 2 3 is are already stored, we can we may able to create chunk number 4, sorry, my bad, like
6.
an additional chunk in
6.
first file, but we won't be able to update anyway chunk number 1 2 3.
Oh, okay.
Because they're immutable, right?
Hmm.
Yeah.
so Praveen, like kind of a Google Doc. Let's take an example of I'm updating it. I mean, I'm not updating at the. I mean, I'm not appending any data. I'm just updating some of the data in between. So in that case, right, then we scrap the whole file chunks and then completely writing into the new chunks. In that case,
Yeah, so I think somewhere Yashini they have mentioned again like the append only part, right? So if it's append only, then the existing one won't be able to update, right? uh, am I
but how does that update works here?
I guess it should involve like scrapping the existing chunk and rewriting all the file
Okay,
altogether,
with the whole design is, yeah, it's bit okay. Yeah, that's what
because the
we can
update
consider.
could be placed anywhere in between. If the updates are placed anywhere in between, then those will no
I
longer
think
be updated.
for that kind of use case, right? This is not being used. Okay, maybe we have to consider that way. Like in between, like kind of Google Doc, right? Maybe the underneath the GFS may not be used right in that case.
Yeah, I think Google Doc. Yeah, I think we discussed it yesterday in initial first few minutes. So Google Doc essentially the collaborative filtering algorithms and all those things, right? Those don't support the like those are more like in place operations or in place changes, right? So here append only won't work with that. So
Correct. That was just
Google Doc kind
this
of
is
applications
yeah,
won't be
one
supported.
use case. That the one use case is only supported append. So when we decide of using GFS, right? So we have to find it. We have to identify whether our use case met this consideration or not. Then and we'll have to go and use.
Yeah, so couple of scenarios could be the ELT pipelines where even if any updates happen in Hadoop or basically any map reduce ones, actually the whole files are rewritten after they call it pre-processing and post-processing state. So if they ever update it, they actually rewrite the whole file with updated file. So the old file is no longer applicable. I think Praveen was trying to point to that because like essentially like being append only, like we won't be able to like retain the existing
Yeah, yeah,
order
yeah.
of
I got it.
uh,
I got it. Yeah.
So can you summarize what we discussed? I'm still not clear. Append I understood, but considering 1 2 3, file 1 is made up of three chunks, 1 2 and 3, and append would be typically considering 3 as the last chunk. It since it won't be, since it is created and won't be up, cannot be updated, it will altogether create chunk number 6 7 and 8. In 8 it will update, or I'm not clear.
No,
So
it
at
will
it,
create chunk 4, 5, and 6, not 6, 7, and 8, right?
No,
Because there's
4
only
and
one,
5
two, and
belongs
3.
to another file, so I'm ignoring
Yes,
that.
exactly. 4 and 5 are in a different. Oh, I see. I see what you
Hmm.
mean. Okay, never mind.
Yeah,
I'm wrong then. So it would be 6, 7, 8, right? If three more chunks go into file one.
Yeah, it should
Okay,
be,
right, right. So you're correct.
because the chunk one will is if it's already full, right?
Yeah.
Then it should be the new chunk.
Mhm.
so to answer your doubt,
ideally then
Lakshmi,
it should not,
uh,
I mean,
so look
only
at it
chunk
this way.
3 should
If
be. Uh-huh. Go ahead.
Go ahead, go ahead, go ahead.
No, my doubt is, if I'm appending, typically it would be end of the file, so only chunk 3 is getting modified, right? So 3 should be scrapped and then move to say 6. Why 1 and
It
2?
will not be scrapped actually here, because it's append only, right? Why do we need to scrap it?
But you cannot scrap it, right? Because it's immutable.
No, no, we cannot modify. Once chunk created, it is immutable. That means,
You can append it, but
yeah,
you
we
can't. You
can
can't
append
append
it.
it.
Hmm.
Yeah. So if the chunk is full, we'll go to the next chunk. If it is not full, we'll update it to that, right?
Hmm. Okay.
I
So
think
one
that
way to look
information
at it
already
is,
master has that information, whether it's a how much it has been written and all.
Okay. Let's read through it. Then maybe we'll understand.
The master periodically communicates with each chunk server in a heartbeat message to give it instructions and collect its states. For performance and fast random access, all metadata is stored in the master's main memory. This includes the entire file system namespace as well as all the name to chunk mapping. For fault tolerance and to handle a master crash, all metadata changes are returned to the disk onto an operation log. This operation log is also replicated onto a remote machine. The operation log is similar to a journal. Every operation to the file system is logged into this file. The master is a single point of failure, hence, it replicates its data onto several remote machines so that the master can be readily restored on failure. The benefit of having a single centralized master is that it has a global view of the file system and hence it can make optimum management decisions, for example, related to chunk placement.
Yeah, pretty straightforward, right? All of these last few points. Shall we move further?
Yeah.
Yeah, go ahead.
Client is an entity that makes a read or write request to GSF. GFS client library is linked into each application that uses GFS. This library communicates with the master for all the metadata related operations like creating or deleting files, looking up files, etc. To read or write data, the client interacts directly with the chunk servers that hold the data. Neither the client nor the chunk server cache file data. Client caches offer little benefit because most applications stream through huge files or have working sets too large to be cached. Chunk servers rely on the buffer cache in Linux to maintain frequently accessed data in memory.
Client cache offers little benefit because of most applications stream through huge files large to be cached. Buffer cache in Linux to maintain frequently accessed data in the memory. Anyone wants to discuss about this and comment? Okay. Yeah, go ahead.
Single master. Having a single master vastly simplifies GFS design and enables the master to make sophisticated chunk placement and replication decision using global knowledge. However, GFS minimizes the master's involvement in reads and writes, so so that it does not become a bottleneck. Clients never read or write file data through the master. Instead, a client asks the master which chunk server it should contact. The client caches this information for a limited time and interacts with chunk server directly for many subsequent operations.
I think this is the point that we were talking initially.
Yeah, that direct arrow between client and the
Yeah.
chunk servers.
Yeah.
So basically, master server never holds the file data, it just holds the metadata. It is not involved in any read and write operations.
We can't say that because even
No, it
updating the metadata also have read and write, right?
no no
But it doesn't hold the
metadata
data.
is fine, but the actual so it is involved in maintaining the information about the file system and the files, but not about the actual data in the file.
Yeah, it's not act as a data storage. Yes, you're right.
Hmm. File name, chunk index, chunk handle, chunk
So
local.
what is chunk index here? Client sends like file name and chunk index it seems.
The, the chunk index is the unique identifier of the chunk. So, okay,
So
maybe I'll
client
give you
already has
generics one
chunk
down.
index.
What is that?
Client already has the information of chunk index.
It file name and chunk index, chunk handle and location. Oh. Can you scroll up? What they talk about chunk index? Yeah, the master client name.
No, they didn't talk here. I think it might be after the diagram.
Yeah, maybe we'll read it. Yeah,
I
that's a good point.
think when we the client generally as a client we when we open the file system, we say sometimes open this file from this byte set, uh, sorry, bytes or offset of bytes from this to this. So kind of that if you want, then you can pass it. If you want the whole file, no need to pass the chunk index. But the bytes specifically, if you want, that I think you can do. So that's why it's saying client passing file name and chunk index.
Could it be also key, like keyword that we want to search in a file?
I don't think so. That's
No?
not a keyword. Shouldn't be a
Okay.
keyword.
Okay.
Oh, I think the library has that information, right? Like somewhere up there, like they mentioned that GFS
No,
client
that
library.
library is only for read, right? It is linked for reading and writing directly with the chunk server.
Maybe we'll read that next paragraph and we'll see once. Okay.
Okay.
It's a bit confusion actually that one.
Yeah.
So that library will be populated by reading it from master. That's what my understanding is. I don't know the name, but yeah, that's what I'm saying. So the library will be populated it But what they're talking about the index? Um,
Oh, you want
but
to read this again?
no, no, maybe the paragraph below this diagram.
Okay.
They might have explained it, right? Each one. So client and JFS client and library. Chunk.
So the data flow is directly between client and the chunk server, while the control is between client and master server. Okay.
Yeah, I mean the rest of the parts are good, but I just
Only
I
this
mean
chunk index.
when I wanted to write, right, what I will write. I mean, I have this much data, um, and my master will give that information which chunk server it has to go. Um, chunk index is yeah, maybe we'll
Not
read it.
talking
Let's see.
about chunk index, lazy space,
Just search
etc.
for Splunk. I mean, not what is that chunk index or search index, control F index somewhere. Yeah. The client.
Ah, here there is.
So the client translates the file name and byte offset specified by the application into chunk index. Yeah, okay, it makes sense now. Actually, it's like file name plus offset. It's a which is an index.
Oh, got it.
Yeah, I think yeah, that's. I mean, usually they're confused as because in the diagram,
Yeah.
right? Because they said the file name plus chunk index. They said in the diagram.
It's a byte offset, basically.
Yeah, it's a combination. Yeah,
File name plus byte offset
yeah,
combination.
yeah, combination.
Okay. This is at the end of the file. Chunk location, chunk. Okay. We were here.
Chunk size is one of the key design parameter. GFS has chosen 64 MB, which is much larger than typical file system block sizes, which are often around 4 KB. Here are the advantages of using a large chunk size. Since GFS was designed to handle huge files, small chunk size would not make a lot of sense, as each file would then have a map of a huge number of chunks. As the master holds the metadata and manages file distribution, it is involved whenever chunks are read, modified, or deleted. A small chunk size would significantly increase the amount of data a master would need to manage and also increase the amount of data that would need to be communicated to a client, resulting in extra network traffic. A large chunk size reduces the size of the metadata stored on the master, which enables the master to keep all the metadata in memory, thus significantly decreasing the latency for control operations. By using a large chunk size, GFS reduces the need for frequent communication with the master to get chunk location information. It becomes feasible for a client to cache all information related to chunk location of a large file. Client metadata caches have timeouts to reduce the risk of caching stale data. A large chunk size also make it possible to keep a TCP connection open to a chunk server for an extended time, amortizing the time of setting up a TCP connection. A large chunk size simplifies chunk server management, that is to check which chunk server are near capacity or which are overloaded. Large chunk size provides highly efficient sequential reads and appends of large amount of data. So basically here they are just talking about like why do we have that 64 MB of size, chunk size.
Yeah.
Why do they even have chunk? Like they're here, they're trying to talk like between 64 MB and 4 KB as an example, but
So master holds the metadata manages. Okay. One is for the traffic, extra network traffic. Other one is reduces the size of store. Okay. Large chunk was extended time.
Yeah, they're, I mean, like with for this, I mean, again, for this application, the use case, right? I mean, the same logic may not be applicable to all the designs, but for this, yeah, we'll have to consider that 64 MB, because they're saying, like, if you open a connection for long, I mean, single connection and open it and transfer the data, right? 64 MB in one shot. So I think we are good. Maybe we can further read it.
yeah. Lazy space allocation. Each chunk replica is stored as a plain Linux file on a chunk server. GFS does not allocate the whole 64 MB of disk space when creating a chunk. Instead, as the client appends data, the chunk server lazily extends the chunk. This lazy space allocation avoids wasting space due to internal fragmentation. Internal fragmentation refers to having unused portion of the 64 MB chunk. For example, if we allocate a 64 MB chunk and only fill up 20 MB, the remaining space is unused. One disadvantage of having a large chunk size is handling of small files. Since a small file will have one or few chunks, the chunk server storing those chunks can become hotspots if a lot of clients access the same file. To handle this scenario, GFS stores such large file with a higher replication factor and also adds a random delay in the start times of the applications accessing these files.
Can we reread and discuss this?
So I think in first paragraph they're talking about what lazy space allocation is, uh, to avoid internal fragmentation. Avoid wasting space. Uh, they just try to the I guess yeah, instead of giving 64 MB, they just try to give the space as needed. So each chunk replica is stored as a plain Linux file on chunk server. GFS does not allocate the whole 64 MB of disk space when creating a chunk. Instead, as the client appends data, the chunk server lazily extends the chunk. So this space, a lazy space allocation avoids wasting space due to internal fragmentation. Internal fragmentation refers to having unused proportion of the 64 MB chunk. For example, if we allocate 64 MB chunk and only 20 MB is filled up, the remaining space is unused.
So basically, it does not allocates a whole 64 MB at once. As and when required, it allocates, and then once that chunk is full, then it creates another one. Okay.
I think the underlying assumption here is like there will be a parallel write operation, parallel append operations coming into multiple chunks at a time, I believe, because or um, because they are talking about um, if a chunk, if they start filling up one chunk, if they don't have enough data, then there is no point in creating a new chunk altogether, right? Why would it create a new chunk if the earlier chunk doesn't have enough uh, or the file size is less than 64 MB?
No,
Like,
but for that one chunk also, it doesn't allocate whole 64 MB at once when it is creating. On the go, it starts allocating the space for the chunk. That's what it is saying, right?
Yeah, it's a what is that in Python, list versus array, right? Kind of, it's not a static allocation. This is like
Mm.
the chunks are.
Mm. Yeah.
I think it's dynamically allocated, but the max size is 64 MB. It's a
So what it does mean that, I mean, when a client make a request to the server to store, get the chunk information, it does not guarantee that, I mean, that request will get succeed. Though it give you the chunk server information, but if it could be possible that by the time you actually start writing or you, your data, there is no enough space on that and your request may get failed. So you have to design, I mean, the client is actually designed with that um, assumption.
so what exactly are they trying to improve here? Like, my question is like, is it just the space allocation or is it just the less fragmentation?
How many times these requests will get fail, and they were okay with that, with the avoid the fragmentation. That was the design choice they actually picked. I mean, with GF as that, instead of actually upfront when master decide that which chunk server will hold this chunk, and they actually allocate, reserve some space on that. And there are a couple of reasons. So one is that, let's say client make a request, client library make a request to master, I want to store the chunk, and master receive that and reserve the space on that chunk server. But that response never reached to your client. So in that case, there is a fragmentation. You will have to, your background job will have to do some extra work to recollect these, reclaim that, and it will take some time. With lazy allocation, you don't need to worry about that. You are just actually writing some metadata, and that's it. Your chunk server space is intact. You are not uh, reserving that space.
So basically, are they caching it in somewhere, like in memory caching on client side or somewhere on the master, or like what? Because like until and unless they buffer some information, it won't be able to like accomplish this, right?
Yeah, so in their design, what they do, I mean, until you, when client start writing, they keep that data and they write it atomically. So that could be possible that chunk master allocate two chunk to the same server, and whoever actually write first will win, and the second, whatever data they copied, that wasted, and you have to rewrite the data again. Does it answer your question?
Um, yeah, actually, I'm trying to relate like how will the like the multiple like how will the competing client request would So actually, I'm finding it tough to relate the competing request with the failed basically failed append operations, or the fragmentation part basically.
The fragmentation part is that, let's say, if they decide that, okay, maximum chunk size is 64 MB, right? So upfront, if you don't know that how much data you are going to write, and you allocate the space, even though you are just writing 1K into that, so you are wasting 64 MB space. So to avoid that fragmentation, they are actually only whenever you are writing, they are actually writing. And I think somewhere in the paper you will see that though the chunk size is maximum 64 MB, and they have a limit for a single request, how much data you can write in a single call. I think it's 16 KB, if I'm not wrong. So that much of the fragmentation, they are okay with that.
Okay.
So somewhere in the
Okay, I
paper,
see.
they will explain, you will get the answer of your question.
So, Pravid, my question is now that means max is 64 MB. The chunk can be smaller than, means that is the max size, but if the file is small, the chunk will be smaller.
Yes.
Okay.
I mean, theoretically, yes, but this system is not as they explain in the, the paragraph you guys were reading, two,
Hmm.
three paragraph above, that this system is not actually designed for the small files,
Yeah.
because you will waste your time. I
Mm.
mean, not time, but the resources,
Yeah.
right?
So
So,
one more
mhm,
point, Praveen, like because all requests will go through the client library, right?
yes.
So that means that the client library, it's a there will be multiple client libraries, or every user has. I mean, in every user place there will be one client. Is it like one client library, right?
That
Um,
client library is that. So they have a static library which your application will consume, and that will be running on your box. And you just interact locally with this client library, but behind the scene, this client library will interact with this backend server.
Correct. That means like for this a
So
config.
each client will have its own instance of client library.
Okay. Whoever is writing a data into this, right? So
Yes,
that should have the client library, right? Yeah.
yes.
Yeah, actually, that is mentioned above in the document. It's 7:04. Should we stop here and continue with the tiny URL?
Yes.
I will stop recording.
Yeah, that's a good idea.